Jai Hind to all. Myself Amita Asthana. Today we will discuss the very important topic from the subject Signal and System, the code being KEC 403, and here we are going to study the systems which are linear and time invariant. So, first of all we will focus on the linear systems and then we will move on to time invariant systems. See, these two properties are very important for the analysis of the systems, and especially if we talk of LTI systems. The LTI systems are those systems that are linear as well as they are time invariant systems. Some few properties we will be understanding in upcoming lectures. In that we will see the systems for the stability and non-stability and causality and non-causality also. But before that, first of all we should understand what are the linear and time invariant systems. So, coming to the property of linearity. The property of linearity holds for any system only and only when the system follows the additivity property as well as the system satisfies the homogeneity property. That means the system will said to be linear only if it holds the additivity plus the homogeneity property. That means both properties together, if they are being satisfied for any system, then the system can be said as a linear system, right. So, additivity plus homogeneity is equal to linearity property. Coming to the additivity property. What is additivity property for any linear system? Let us see, let us say I have one input, that is xt, and the input has been passed through a system, transfer function is given as t, and this t of xt is equal to yt, let us say, and if I take more inputs to the system, let us say t of x1t is equal to y1t and t of x2t, some another input we are taking as x2t, is equal to y2t. That means there are two outputs. The y1t output is corresponding to the input x1t and y2t is corresponding to the input x2t. So, if I want to add, let us say if I want to add these two inputs and addition of these two inputs yields the addition of y1t and y2t, then we say that the system is a linear system. That means, that is, the system is linear only when t of x1t plus x2t is equal to y1t plus y2t. That means this property that clearly states that if addition of the input is given to the system and the output is the addition of the individual outputs of the corresponding inputs, then only we can say that the system is a additive property system. that means the system is satisfying the additivity, then only we can say that the system is satisfying the addition property for the given inputs x1t and x2t. So, let us say coming to the example for additivity, let us say I have one system that output is the differential of any input xt. So, what I can do to satisfy this additivity property, let us say here suppose I have one system y1t and this is the differential of x1t, okay, and I am having this y2t that is differential of the x2t. If I give the input to my system and I say that I need to calculate the response for my x1t plus x2t, then it will be obviously differentiation of x1t plus x2t. So, here I can say that my additive property is being satisfied, So, if I give the combined input, I am getting the output that will be y1t plus y2t. So, my system is additive for this yt is equal to dxt upon dt. Now, coming to one more example, let us consider the yt is equal to 2 of x square t. So, let us take two inputs x1t and x2t and the corresponding outputs would be y1t and y2t. That means here my yt is equal to t of xt if this is nothing but 2 of x square t, and if I write my y1t, that should be 2 of x1 square t. That means my t y1t would be 2 of x1 square t. Coming to the next output, that is y2t, okay. That means that would be 2 of x2 square t. So, here I must write instead of this 2 of x1t, and I must write this yt is equal to 2 of xt and y1t of t of x1t, that is equal to 2 of x1 square t, and y2t is equal to 2 of x2 square t. Now, my next step, that means it can also be written as t of x2t. Okay, that means we understand by simple point that whenever I am giving x1t as input, my x1t is getting multiplied by 2 and it has been squared also. Similarly, if I am giving x2t as input, then my x2t is getting multiplied by 2 and it has been squared also. That means the two actions are taking place for x1t as well as x2t, and the corresponding outputs are y1t and y2t. Now, the next point, when I give the x1t plus x2t, okay, so here please see carefully that whenever I give x1t plus x2t as a combined input, I give x1t plus x2t, that means what will be the output then? The output will be clearly 2 of x1t plus x2t square. That means here this is 2x1 square t plus 2x2 square t plus 4x1t into x2t. So, here I can say this term is matching with this term is also matching with this one, but this is coming out to be an extra, and hence I can say that t of x1t plus x2t is not going to be equal to the individual sum of the outputs for the corresponding inputs, that is y1t plus y2t. So, here this system clearly proved to be non-additive. Non-additive system. So, if this is non-additive system, that means it should be non-linear also, because I am having two properties together, then I can say that it is a linear system. Since this system is non-additive, so it can't be a linear system. Now, coming to the next property for linear system, that is homogeneity. What is homogeneity property? So, we have understood the property of linearity. Now, we will focus on the property of homogeneity. What is homogeneity? So, here what we can mention is that homogeneity property, let us say I take one system that t of x1t, let us say any input x1t, the corresponding output to be y1t. Okay. Now, if I multiply with some constant to my input, this constant I am multiplying to my input, this is a constant, and this constant, if it is reflecting at my output, then my system is homogeneous system. So, this is the homogeneity property for any linear system, and if my linear system is satisfying both the properties, then only it can be said to be a linear system, otherwise it is not a linear system. That means, again I am repeating that linear system is equal to homogeneous system plus the linear system. So, additive system. So, addition plus homogeneous is equal to linear system. Now, coming to another property, that is time invariance. What are time invariant systems? So, the time invariant system, if I am having this output yt that is coming from any input to the system, and that we can represent it as t of xt is equal to yt. So, t of xt is equal to yt, then if I shift my input, by some tau, then the output is also being shifted. That means, shifted input yields a shifted output, then I say my system is time invariant system. Any change, any shift in the time for my input is reflecting on the output with the same change, then I can say that my system is time invariant system. So, let us see by some simple example. I am having this example, yt is equal to minus infinity to t x of tau d tau. This is my output for the given input. That means, whenever I am giving some xt, the system is taking the integration from the limits minus infinity to t, and then the system is yielding the output for the corresponding input. So, my next step is how I will check the time invariance property for this particular system. So, what I will do is, the concept is that I will shift here. I will shift my sequence by, let us say, t minus tau minus t naught. If I shift my sequence or input by t naught, then my output should be shifted by the same time unit. Then I can say that my system is time invariant system. So, let us do that. So, here in that case, let us assume that I am having some another output. If I shift my input by t naught units. So, here it is tau minus t naught d tau. So, here I need to find out the relationship between this y bar t to yt. If this y bar t is the shifted output, then I can say my system is a time invariant system. Let us see that. By assuming, again I should rewrite this y bar of t is equal to minus infinity to t x of tau minus t naught d tau. Let tau minus T naught is tau bar. Okay. Then I can say my d tau is equal to d of tau bar. Okay. Now checking for the limits, what I can do for the limits, that I will do later. First of all, I must write this y bar t. We will check the limits. That should be x of tau bar d tau bar, and here the if my tau is tending to minus infinity, then tau bar is also tending to minus infinity. That means here the system limits will remain same. Similarly, for tau tending to t, tau minus t naught, let us say if my tau is tending to t, then my tau bar is tending to t minus t naught. So here I will put my limit as t minus t naught. So for this I can say that this particular integral becomes minus infinity to t minus t naught x of tau bar is same as this d tau bar, and my output that I can say here it was by bar t. Now here I can say that it has been shifted as t naught unit. Wherever it was t, now the output has been shifted to t minus t naught. So that clearly states that as I have shifted this t minus t naught, my output is also changing. So d tau x tau bar is nothing but tau minus t naught, and d tau is equal to t bar, and hence I can write this as equal to, I must rewrite this, y bar t is equal to minus infinity to t minus t naught x of tau bar d tau bar. So what I can say is this is minus infinity to t minus t naught. Since tau bar is nothing but tau minus t naught, so x of tau minus t naught, d tau is same as d tau bar, so I can write it as d of tau, and here I can say that this is nothing but my by t minus t naught. So this property states that the system is clearly a time invariant system. So we can prove similarly for another time invariance properties for the system. Thanks for this lecture.